Good morning. So let's start chapter 8 today with one of the nicest lessons in this class and one of the most useful ones in real life, even beyond the goals you may have with finite mathematics for your major. So it's something that sometimes is frustrating if you still don't get the hang of it in the beginning, but I strongly advise you to be patient with yourself. Go slow with this. Make sure you really understand the main idea behind the whole concept of what we call in this lesson the conditional probability, because this is again one of those skills that are useful in life. Even if you don't actually solve probability problems, this insight of a conditional probability is extremely useful when you want to figure out the odds of some random events. And in life you always have to face such odds, no matter what. So therefore, it would be nice to have a good intuitive sense of the real likelihood of some events to happen, given the information you have. We will define in a formal way pretty soon what the conditional probability is, but this is one of those topics that are best understood if we start with an example, or two examples to be more precise. Two examples that you'll see are kind of at the extreme of each other, that I hope illustrate what we mean by a conditional probability. So before we even define the concept, let's take some time to write these. So write it down on your notes, what you just see here on the screen, and then we're going to explain what we mean by this. So think of this as two examples side by side. Okay, so this is the example one of a situation, and this is example two. And I'm going to actually start with example two because that's going to be the easier one to understand in terms of the what the answer is. So the experiment in the second example, right, it says that a coin is tossed and a die is rolled. And in each example, I'm going to ask two questions. Okay, so once again, in this experiment, you toss a coin and you roll a die at the same time, or one after the other, it doesn't matter, right? But the experiment means, tossing the coin and rolling the die at the same time if you want. And then we'll pose some questions related to the outcomes. So here's question one. What is the probability that you rolled a 6, right, when you roll the die? Well, remember the possible outcomes when you roll the die are 1, 2, 3, 4, 5, and 6. So as far as the die is concerned, there are two possible outcomes. For the coin, the outcomes are heads or tails, right? So if my question is what is the probability that you roll the 6, I hope nobody will actually disagree that the answer is 1/6. Okay, that's pretty straightforward. 6 possible outcomes. If you want a probability of rolling a 6, that's just one outcome out of 6, so it's 1/6. Now pay attention to the question 2, which may sound actually silly, but hold that thought for a moment. What if I ask, what is the probability that you rolled a 6 given that, so this time I'm providing you basically additional information, given that you tossed with a coin a tail. So you may ask yourself, what's the point of this question? It sounds kind of silly, right? I mean, what does the coin have to do with basically my chances of rolling a 6 when I roll the die? And so hold that thought for a moment, especially when we move on to what we call later independent events, because obviously this additional piece of information in this example is pretty much meaningless. I mean, not meaningless, but irrelevant for the question at hand, right? So obviously the probability, the answer for the question asked is the same, 1/6. What the coin did or what happened to the coin has absolutely no bearing in the outcome of rolling the die. So you could say that in question 2, this extra piece of information was really irrelevant, right? So the probability of rolling a 6 with the die was still 1/6 in both cases. Okay, so I hope that's clear. And now let's move on to the first example, which is actually the one conducive to the notion of conditional probability that we'll talk about in a moment. So this elongated rectangle here, let's suppose this denotes denotes a group of students. 100 students to be more precise at a certain university. And then let's say we have the breakdown by sex. We have 40 girls and 60 boys. And of these 40 girls, suppose 20 of them are freshmen, and of these 60 boys, 10 of them are freshmen. So I hope the picture is pretty clear here. So I indicate this freshmen, this overlap with both girls and boys. 20 of them are girls, 10 of them are boys, right? The freshman group, so to speak. And in this case, I'm going to ask again the same, I mean, not the same, but again, two different questions. So question number 1, and I did actually mention the experiment, but let's say a student is picked at random. You randomly pick a student in this group. So here's question 1. What is the probability that a freshman was picked? All right, so in this case, well, we have a total of 100 students, 40 plus 60. So we have a total of 100 students, of which 20 girls, 10 boys, of which 30 are freshmen. So then the answer to this question is 30 over 100, which we can simplify to 3 over 10. All right, so now, finally the punchline. Let's look at question number 2. What if I say that, what if I ask, what is the probability that a freshman was picked, given that a girl was picked? All right, so notice that in this type of language, in this second question, in both the second example over here and this one here on the left side of the page, what follows after given that? So what follows after the words given that is extra information, an extra piece of information. So is that relevant? Well, in this case, after a quick look, the answer should be obviously yes, because now if we do know that a girl was picked, all of a sudden the number of outcomes possible from which you actually compute this probability is collapsed to 40 items only, or 40 girls, in this particular example. So it's not a matter of picking 30 freshmen out of a total of 100 students. It's actually a matter of picking just 20 freshmen out of 40 girls. So once we collapse, once we have this given extra information, this becomes relevant, right? Because we know that no boys were selected. So I don't even look at the 10 freshman boys. I don't even look at those because again, that's not part of the data anymore. Once I know that the girl is selected, I'm only looking at the freshman girls with respect to the total number of girls. So is this piece of information relevant? Yes, it is relevant because in this case, of course, the answer to the probability whether you picked a freshman or not is going to be 20 over 40. So in this particular case, the way I actually give the data, it's a much bigger probability, is 1 over 2. So this is my main motivation, and I'm going to give you actually another example from real life before we move on to our second page. But this is, if you want, one of the best motivations you could have for studying conditional probabilities. The odds can change quite dramatically if it so happens that the extra piece of information, the condition, if you want, when you formulate the probability question, is relevant. So you could have much higher odds or much lower odds depending on the data in the problem. This is why sometimes people, incorrectly are sometimes shamed for worrying about, for instance, whether they are afraid of accidents or some bad things that can happen and let's say when they fly a plane or whatever, because in many cases, well, sometimes of course it's because unfounded information. So for example, people being just afraid to fly. It's not like they have to be shamed, of course, but it's just incorrect information, right? Because the likelihood of an accident in the plane as a whole, it's a very low probability. However, when certain things happen, often people actually, without even realizing, they actually pose themselves these type of conditional probabilities. So let me give you a quick example before we move on to finally formalizing the notion of a conditional probability. Some of you might know this. A couple of years ago, there were some incidents of battery fires. I mean, there was a new plane. In fact, let me actually write down the quick story. One of the newest planes made by Boeing, 787, the replacement for 777, so the newest mid-size jetliner. So there were, I think, 2 or 3 incidents of battery fire. It didn't end up being a serious accident, but potentially dangerous, right? Anything that catches fire on a plane is potentially a serious business. So unexplained battery fire, so like the battery is melted down or something like that. Okay, so you have one case of a battery fire, one case at a certain moment, and then let's say I forgot exactly the time between the events, but let's just say 1 month later, then another case of a battery fire. All right, so I mean, if for example a question will be, forget about the brand. I mean the type of the plane here, the exact type of the plane, Boeing 787. But if the question is, for example, given or if in a regular flight, what is the probability of a battery fire, then maybe the answer, I don't know what it is, maybe it's very, very low. Right, so there's no reason to think that this is a big likelihood. Anything can break down. There's no such thing as zero probability, but probably an extremely low probability. So of course that will be the answer. But especially after these incidents happen, if the next question would be in a regular flight, what is the probability of a battery fire, and here's come the punchline, given that you fly a Boeing 787, obviously it's a bigger probability. At least at the time. Now the issue is fixed, more or less anyway. That's a different story. But the point is, when people, for example, are afraid of incidences like that, especially if one or two happen like that, they think in terms of conditionals, in the sense that they assume something else goes on. So they assume something about after the words given that maybe the plane is faulty, given that maybe the plane or this particular brand of the plane has an issue with a piece of equipment, so on and so forth. So then all of a sudden you have an extra piece of information which changes the number of outcomes and the number of total possible outcomes, right? I mean, it's a completely different fraction, which, like in the previous example here, can lead to a different, larger value in this case. Okay, so I hope that's clear. Conditional probability simply means, and let's write it down before we move on to the second page. Conditional probability as a concept, it's all about using extra information if available. And on top of that, this concept of a conditional probability allows us also to compute other probabilities which are otherwise not easier to compute. Sometimes certain probabilities, as you will see in this lesson, can only be computed via conditional probabilities. You have to construct conditional probabilities to compute the probability of an event that you may want. But roughly speaking, this is all there is to it. I mean, you don't ask just the probability of an event, you ask the probability of an event given that a different event already happened. That's what we mean by the extra information. So stay tuned for the second page so we can move on to a math formulation of the whole concept. All right, so like I said before, we want to formalize how to compute the probability of an event E given that another event F already happened. Okay, so basically the notation, so this is basically what we call conditional probability. Conditional probability. Right? The probability of an event E given that another event F already happened. There's a special notation for this. So the notation, which you'll have to get used with it from now on, is the probability of E vertical bar F. Whatever comes after the vertical bar is given that. So you read this, P probability of E given F, given that F already happened. So we already kind of illustrated with the example with the boys and the girls before, but just to make it clear how that goes, imagine that you have these events kind of overlapping like this in some sample space S. Okay, so this is event E, this is event F, this is the common part of them. And remember the notation N of S, N of E, N of F, these are the number of elements, right, in each set. So, for example, if someone will ask you what is the probability of just the event E, of course you look at the number of outcomes in the event E divided by the total number of outcomes in the sample space. However, and I hope it's pretty obvious from the picture here, so we're going to write it down over here. If I ask the probability of the event E given F, so pay attention here, if the event F already happened, then your universe is reduced to the outcomes of F. You only look at the outcomes in F. You're not going to divide, so the denominator is not going to be any more the number of elements in the whole sample space. There's no point in doing that. Once we know that the event F happened, basically all the possible outcomes are those in event F. And in that condition, when you ask yourself what is still the probability of E to happen if F already happened, well, you only look at the portion of E which happens to be included in the event F. So on the top, you no longer have the number of elements in E, but just the number of elements in E intersected with F, just the common part between E and F. You reduced to the universe of outcomes in F once again we know that event F happened. So if I divide both sides by the number of outcomes in the whole sample space, you could see how the formula, so the main formula for computing conditional probabilities is going to be, and there are very different ways to write this down. So it's P of E given F is the probability of E and F divided by the probability of F. And it's useful to write the equivalent one side by side. So what if I want the probability of F given E? We just interchange the role of F with E. The numerator is the same because F and E is the same as E and F, so there's no reason to write it in a different order. But on the bottom, of course, is the probability of E. So these are given in the formula sheet. Keep this in mind. Sometimes it's more practical to combine them into a single formula without fractions. So we can write this down as a formula for the intersection of two events. So P of E and F, you can write it as probability of F times the probability of E given F, or you can write it as probability of E times the probability of F given E. So keep this in mind. These are extremely useful formulas because you will see that in practice often we can actually compute the conditionals first and not the left side. So often in many problems, as you'll see even today, it's not going to be possible to compute directly the probability of the intersection of two events. But if you write it in terms of conditional probabilities using this formula, then you could actually solve the problem. So for now, for the rest of this page, I just want to go over a couple of quick examples so you can see how this formula works. And then we're going to move on to some word problems just to see how how it works in some cases. So all right, so let's see an example. So suppose that P of E and F is equal to 0.3 and P of E given F, so you are given a conditional as well, let's say it's 0.5. And then the question is to find the probability of F. So here you can use one of these formulas. So P of E and F, you can write it as the probability of F times the probability of E given F. Make sure you pick the right formula. And you are given P of E and F 0.3, just plug it in the right position. And P of E given F is 0.5. So then just divide by 0.5 and you get 3 over 5, the answer for the probability of F. Here's another one. Let's say P of F is equal to 5 over 13. P of E given F is equal to 4 over 5. And let's say we need to find the probability of E and F. Once again, it's a direct application of this formula. You can write again the formula. That's P of F, P of E given F. You got to be careful whether it is this or the other one, right? I mean, depending on whether you start with P of E or P of F, right? So, but if I start with P of F, then the next conditional should be E given F. If it's P of E, then the second factor here is P of another event given E. So the order matters of in this conditional probabilities. All right, so let's plug in what we are given in the problem. P of F is 5 over 13. P of E given as is 4 over 5. We can cancel 5. 4 over 13 is the answer for P of E and F. Okay, so the real, like I said, some word problems are more illustrating of why actually these conditions are so useful. So let's see. Yeah, I mean, I'm gonna squeeze in a quick example before we move on to some other ones in this page, which is again illustrating of why conditionals are so important. So, for example, let's say in a group of, okay, let me put the question first, and then I'm going to illustrate with some numbers. So, for instance, if you look at the health data, let's say one will ask, what is the probability? So, two questions, right? So, the probability of a randomly selected person to let's say to get lung cancer. I'm trying to find some less dark examples, but there are not too many actually in the when it comes to health data. And if you want to illustrate, you know, some examples of this sort. And then the second question, the probability of a randomly selected person to get lung cancer in his or her life if he or she is a smoker. Okay, so that's basically a real life example, if you want, when the intuition is pretty obvious, right? So the answer in question 1 is going to be smaller, right? A lower probability than the answer in question 2. Okay, if you were to look at the sample space, and I don't want to put this on the next page, so I'm going to maybe squeeze it here in this corner. You would imagine basically the population split into smokers and the other group non-smokers, like that. But the overlap between these two categories, when you count the people who get lung cancer eventually, there's going to be a much bigger overlap probably over the smoker population. So basically that's an example analogous to my first one with the freshman, right? When you select a freshman. Because, you know, in that case, it was a little bit artificial. And I said, okay, a randomly selected person, what's the probability that person is a freshman, given that you selected a girl? So why would you select a girl in the first place? So, I mean, that's kind of an artificial thing. So, I mean, that extra piece of information. But for example, in health data, this extra piece of information obviously is available also from other sources. Let's say you look at the table of data that basically estimates the number of smoking population, right, in a certain town or country. And on the other hand, let's say you have the number of lung cancers and then you have an overlap between smoking and non-smoking. So therefore the probability, the conditional probability will be obviously much higher because the overlap will be much bigger on the smoker population, right? Since of course smoking is one of the causes, major causes of lung cancer. Okay, so I hope that's pretty clear when the extra piece of information is relevant. So with that, let's move on the second page with the, next page with some other examples. So stay tuned. Okay, so let's take a look at another example, another default example that is very useful in when we learn probability theory. The famous colored marbles box. Okay, so suppose, and write this down, suppose we have a box with 2 red marbles, 4 green, 1 black, and 8 yellow. And pay attention to the way I formulate the experiment and then the subsequent questions based on the experiment. Let's say 2 marbles are selected without replacement. Okay, so basically the experiment means that you pick one, put it away, and then pick another one. So let's ask a variation of questions here. These are basically, just to anticipate a little bit, these are examples in which you kind of must use conditionals. We must use conditional probabilities. Even though the problem does not ask you to do that. So here's first question. What is the probability that the first marble is green and the second is red? The first one is green and the second is red. So why would you need conditional probabilities? And let me actually write down the formula again to have it in front of me here. So P of E and F is P of E times P of E given F. Well, the short answer, because by the way, if you notice here, the word and is used, right? So that means I kind of have to use I have to think about the intersection of two events, right? The first is green, that's one event. The second is red, that's the second event. And if I have and between them, that means I have the intersection between two events. Now, why would I have to use conditionals here? Well, because the key word here is that it's without replacement. Once I pick a marble out of the box, I'm going to change the conditions on the remaining marbles in the box when I ask what happens with the second marble when I pick it up. And depending on the questions I ask, the color, for example, of the first and the second, and in general, the number of marbles, all of these change the conditions. So of course, the way to figure this out is to actually use conditional probabilities, because we have to assume something that happens with the first marble so that I can compute the odds of the second event given what happens with the first marble. So just to write it down in the language of probability, the question is, and I'm going to try to use as few words as possible to be more compact. So the probability that the first is green, so green first and red second. Well, if I use this formula here on the left, I can write it in terms of conditionals in the following way. The probability of green being the first marble times the probability that red is the second given that green is first. Okay, so we simply restate the probability of the intersection of two events using conditional probabilities. So what is the probability that the green is first? Well, we have 4 green marbles, and in total we have, if I add up 2 plus 4 plus 1 plus 8, that's 15 marbles. And really pay attention and slow down or pause if you want. What is the probability that the red is the second one, given that I picked a green one? Well, if I pick the green one, I still have 2 red marbles in the box, but out of a total of 14 marbles only. Because again, it's without replacement. So I picked one, put it out, there are 14 remaining, of which 2 are red. So the probability that the second one is red, given that the first one is green, is going to be 2 over 14. And the product of the two is the probability of green first and red second. So if I come up with, let's simplify this a little bit, that's going to be 4 over 105. Okay, so I hope it's clear. Let's answer another question. In fact, here's an exercise for you. I'm not going to explain it, just pause before I put the answer here. What is the probability that you have yellow first and green second? Pause for a moment. Your answer should be, really pause, try to answer. Okay, so then after that, it's going to be 8 over 15. Yellow first, green second, 4 of them out of 14 only. So once again, we can cancel a 2. That's going to be 16 over 105. All right, so let's do the third one together. And there's going to be a little bit of a twist here. I mean, a little bit different than the previous 2 examples. What if I ask the probability that green is first and also green is second? So what is the probability that the first one that I take out is green and the second one is also green? And so notice, again, we can write this with conditional. So this will be the probability of green first times the probability of green first given the first one is all probability of green second given that the first one is also green. So the probability of green first times the probability of second one being green, given that the first one is also green. So again, the first probability here is going to be 4 over 15, right? We have 4 greens. But now pay attention what happens if we assume that the first one is green. So if the first one is green, first of all, just like before, there are only 14 marbles remaining in the box. But because we picked the green one, then there are only 3 green marbles left. So the second probability in the product will be 3 over 14. And again, when we simplify this, let's see, we can simplify this by 2. We can simplify this by 3. This will be 2 over 35. So that is the probability of picking green and green in the first and the second attempt, again, without replacement. Slightly trickier examples of this type are ones in which we have to split the probability that we ask into mutually exclusive events. So what if I asked the following? What is the probability that one is red, either the first or the second. So one is red and one is green. Okay, so let's pause for a moment. These are usually the trickier ones until you get used to the whole concept. Because your first question is, okay, it looks from the previous example that I better know what I picked in the first attempt so I can figure out the probability of the second marble. So the question here is that one is red, one is green, but it doesn't say which one, the first or the second, because it doesn't matter. And the question is, what are the odds for either of these two to happen? This is your indication that you should split the event, split it into two mutually exclusive events just to answer your own question, right? So I need to make an assumption which one is first, which one is second. Since the event that I have to compute doesn't care, so it's either red or green or red, well, let's just compute that basically because these are mutually exclusive. So two things can happen. Two things can happen to realize this, this event, one red and one green. Either the first is red and the second is green, or the first is green and the second is red, and the two are mutually exclusive. They can't overlap. It's one or the other. And remember, the probability of the union of two exclusive events is the sum of the probabilities. So basically, the probability of the event in this question can be written kind of like this. Red first and green second, union green first and red second, right? You don't have to write this down to make it overly complicated, but I want to point out that you're basically asking the probability of two mutually exclusive events and the union of two mutually exclusive events. So basically, as we know from the previous formulas, the union of the, in this case, is the sum of the probability. So you compute the probability of red first and green second plus the probability of green first and red second. And now each of them can be written in terms of conditionals. We kind of compute them actually on the top, but I'm going to do it one more time just in case. So the first one is probability of red first times the probability of green second given red is first, plus the second term, which is the probability of green first times the probability of red second given green is first. And now we can finally compute them. So the probability to pick a red in the beginning is 2 over, because there are two red balls, right? Red marbles, 2 over 15 times green is 4 of them over 14, plus the probability of green first, which is 4 over 15, times the probability of red second given the green is first, so that's 2 over 14. Once again, we can simplify this a little bit by 2. So we're gonna have 4 plus 4, which is 8, divided by 105. And that's the probability of question 4. So let's do, yeah, I think I'm gonna do this. It's not gonna look too good, but I think I'm gonna do it on the second page. There is just one more question based on this problem. Actually, let's do it here because I want to start with a clean sheet. It's not gonna look too cute on this last part here, but I just want to put one more question here. So here's another example when you have to compute to make it a disjoint, union of mutually exclusive events. What if I ask the probability of second to be yellow? So if you notice here, I don't care what the first marble is, what color is, right? I just ask what is the probability that the second one that I picked from the box is yellow. That still requires conditional probabilities because it matters whether I pick first a yellow or not. That affects the odds of picking a yellow on the second attempt. So basically, the way you split this is to say either I have yellow first and yellow second, or not yellow first and yellow second. Okay, so let's write it directly with probabilities because I don't have much room here. So probability of yellow first will be 8 over 15 and times the probability of yellow second. But if I picked a yellow first, that means I have only 7 yellow remaining out of 14 marbles remaining. On the other hand, the other version is that I don't pick a yellow first, but what's the probability of not picking a yellow? So pay close attention here because that's the probability of a complement. So if you go back all the way to the box, if you pick a non-yellow marble, the probability of a non-yellow marble will be all the other outcomes, 2 plus 4 plus 1. That will be 7 over 15. And then you still have 8 yellow remaining and only 14 marbles in the box. So that's going to be, let's see, let's simplify again by 2, 4, 7, 4, 7. That's 28 plus 28 makes it 56, divided by 105 again. All right, so make sure we bring questions about these situations when you have to split it into mutually exclusive events, because these are sometimes trickier, these types of questions. So I'm going to finish with another page. I want to go over another problem with conditionals based on a table. And with the elections coming up, this is probably a very nice example to finish the lesson now. I wonder actually if this is going to be, probably, yeah, this is going to be covered before the election anyway. So stay tuned for the last page. All right, so take a moment to write this table here with these labels. Let's say we look at the population in a community split by sex and by the political affiliation. And let's say we have Democrat, Republican, and Independent, 3 political categories. So let's suppose that so let's say this is like kind of like a bluish tint of community. We have, let's say, 50 Democrat males. So in the table you put the number of in each category, right? So 50 male Democrats, 60 female Democrat, 40 male Republican, 30 female Republican, and let's say I want to actually use nice numbers so that I have a summation, at least the denominator nice. Let me think a little bit. So I have 110 plus 70, 180. Let's say even split between independents, 10 and 10. So in problems like this, by the way, it will be useful to make totals before we even look at the questions here, because you will see the totals matter. So underneath, notice that we have 110 Democrats altogether. We have 70 Republicans. And we have 20 independents. And then here we can also make totals by gender, by sex. We have, let's say, 100. It's kind of 50-50. I should have chose different numbers so that I don't have, but that's fine. So 90 plus 10, 100 male, and then also 100 females. So obviously population total is 200. If you do this correctly, obviously the summation by rows like that should be the same as by the column, right? So total number of females and males, that's the population total. The summation by the political distribution should also be, 200 because it's the same number of people. So let's say the experiment is that we pick basically person at random, and we have a various events here. So let's say M is the event that says the resident that you pick is a male. F is the resident is a female. D, resident is Democrat. R, resident is Republican. And then I, resident is independent. Okay, so let's ask a couple of questions here. So for example, what is the probability of a female given that the female is independent? Female given that she is independent. So in problems like this, you don't actually need to use formulas. I want to make it clear, we can use the formula just for the fun of it. Because remember, the formula in this case is the probability of F and I divided by the probability of I. Just for practice, we could do it this way, but you could do it directly from the table. So directly from the table is that once I know, you look at the given part, okay? So you start with the given part. If I give you that you picked an independent, so this is the probability of female given that she is independent. Once I am given that I picked an independent, I only look at the last column. I only look at the independent column, everything else doesn't matter, and I look at the distribution between females and males in that independent column. So just directly from the table, I can tell is 10 over 20, which is 1/2, the probability that a female is independent. There's no point in using the formula. Not that the formula doesn't give you the correct answer, but it's kind of, not an overkill, but it's just not necessary to go via the formula. If you want to do it just for practice, the probability of F and I, well, we look at the intersection between females and independents. So that's going to be 10 exactly. So of all the people in this community, there are exactly 10 females independent, divided by the total number of people, which is 200. So that'll be on the top, the probability of F and I. And the probability of just independent, well, there are 20 independents. See, this is why it's useful to make these totals. 20 independents in the community divided by total number of people, 200. So the 200 obviously cancels. It's 10 over 20, which gives you obviously 1 over 2. But in general, when the data is given by tables, you can compute all this probability easily. You just have to pay attention to see whether you add up by column or by row. So here's another example. What will be the probability of, let's switch this. What is the probability of picking an independent given that she is a female? So pay attention here. If I give you that I picked a female, then the number of possibilities are on the last row, right? So I picked a female, meaning that the total number of outcomes relevant now are 60 plus 30 plus 10. You already computed the summation, it's 100. And of these, the number of independents is 10. So it's going to be 10 over 100, which is 1 over 10. What about the probability of, let's put another couple of more. Democrat given a male. How many males in total? 100 males. So given a males. How many Democrats among the males? 50 Democrats. I picked another 1/2, right? So it's going to be 1/2. What about the probability of a female given that she is Republican? Well, given that she is Republican, all of a sudden, total number of outcomes are 70, the total number of Republicans. And the probability that of a female in that group, well, there are 30 females among the Republican group, so it's going to be 30/70, which is 3/7. Okay, so these problems, once you understand them, the ones with the tables, should be pretty easy. Just make sure you look carefully at what's given so that you can restrict your analysis just to one row or one column of that table. So take the time to go over the homework, and as always, remember to bring the questions to the Zoom sessions before you move on. And that's it for today.